just started on the quotient rule had made mention that those are two rules that you're going to need to be familiar with. They're two that you're going to need to have memorized to some extent. Thank you, Laura. You're going to wind up memorizing it whether you want to or not because you're going to use it so often. Okay. Does anybody happen to recall if you have something like y equals f of x times g of x, what the rule is for computing the derivative of that? Well, first off, can you just do it straight out and do it as f prime times g prime? Does that work? No, that would be if there was a plus in between them, and then you would have f plus g, and that would work. But because they're multiplied together, you have to use the product rule, okay? Which goes f prime g plus f g prime. Now, I've seen more than one person ask over the years, is this the same thing as f g prime plus f prime g? Are those two things equal? Yeah, okay. They're the same thing. House back there, yep, they sure are. Why are they the same? Why can you use either of those?
Because the numbers don't really change. You just change which side of the plus sign they're on.
Yeah. Okay, it's like 2 plus 3. That's the same as 3 plus 2. It's the commutative property of addition from way back in ancient times, probably in 7th grade somewhere. I didn't think I'd ever need that again. Okay, it allows you to make that reversal of the terms when you're adding. So don't worry about it. If you've seen this before or it happens to stick in your mind the other way, it's fine. This is okay. Okay? No problems. All right, so let's take a look at something that would require the product rule. Let's say we have something like x squared minus 9x times, let's say, x to the 5th plus 6x squared minus the square root of x. And you're asked to compute the derivative of this. Now, one approach that you can use, you get on the test and you have a brain cloud. Happens to all of us at some time or another, and you look at, I just did 53 of them, and they all worked. I don't know what's going on now, but it's not working. Okay, what do I do? Well, one way that you could do this, and I'm certainly not encouraging this because it gets a little lengthy, is you could take and distribute the x squared times each term, and then distribute the minus 9x times each term, multiply that mess out, and get some big long polynomial of sorts. And then just do it term by term by term. Doesn't look very pretty, does it? Okay? It is one way to do this. Okay? Another way to do this is to use the product rule. How do you know you're using the product rule for this? Well, the two things are added, subtracted, multiplied, or divided together. They're multiplied, aren't they? And if they're multiplied, you're going to end up with a product, so you use the product rule. Oftentimes in math, the name of whatever the rule or property is describes what it's for. The product rule is the rule for computing products. Okay? So, what I would encourage you to do is to come up here and label each of the factors. We'll call this one f and this one g. We'll lay out a plan. We'll do f prime times g plus f times g prime. I'm hoping you're getting into the habit of writing that out or got it memorized and it's in your head even if it's not on the paper. Is that making sense to everybody? Okay? And you just take it one piece at a time. Now, sometimes folks like to cover their points and get as many points as they for sure can get. In other words, put down the easy parts of it. Well, a real easy part is just putting down the plus. Another real easy part is just copying down what g is. Well, that's x to the fifth plus 6x squared minus the square root of x. And over on this other side, well, I can copy down this x squared minus the 9x. How much calculus have we done so far? Nothing. And that's part credit. Make sense? You're part way done. Now, will P and G pay you on partial credit? No. Enjoy it while you're here. Okay? The real world doesn't work on partial credit. It's more binary. Either you did it or you didn't. Not you sort of did. Okay? So enjoy it while you have it. Okay, so let's now take a look at what's left to do. F prime. Well, that means to look at that first factor, this one, and compute the derivative. What's the derivative of that factor? 2x minus 9. There you go. You're doing the calculus in your head. 2x minus 9. And the other thing we need to work on is g prime, which means compute the derivative of that. 2 of the 3 you should be able to do quickly in your head. Do you see we're going to get a 5x to the fourth plus 12x. Does that make sense to everybody? Minus, now remember, and you'll get the hang of this as well, square root of x is x to what power? 1/2. Most of you look to have your exponents in good working order. A couple of you struggled on the quiz on it. It's okay. They're not going to go away, so you'll get good at it. So there's the good news. Okay, they're not going to go away, so you will get lots of practice. Taking the derivative of this means we'll drop that 1/2 out front. We'll have 1/2 x. Then you take the exponent and subtract 1 from it. 1/2 minus 1 is negative 1/2. And you know what? Walk away from it. You're done. Don't try and simplify it. Don't try and multiply it out and combine terms and all that stuff. You will not get any extra credit for trying to simplify it. You won't gain any points, but can you lose points? Yeah, because if in the process of trying to simplify it, you make a mistake, points out the window. Okay? Get it to this form and walk away. Just keep your hands off of it. Okay? Does that make sense? Okay? Okay, so there's the product rule. The other thing that we introduced was the quotient rule. Very soon we're going to work on something called the chain rule. And with the chain rule and the product rule, you can kind of work around the quotient rule. But the nice thing about the quotient rule is when you come across functions, you can look at it and say, okay, do I want to rewrite this as a product rule and know that I'm going to do product and chain rule, or should I just take it with the quotient rule? You've got options. Okay? So what's going to wind up happening very soon, section 1.7, is we're going to pick up yet another technique for computing derivatives, and it'll give you a second strategy for dealing with rational functions. It's nice to have a choice in things. If we have something like y equals one function over another function, the derivative is going to be f prime g minus f g prime over g squared. Ho d hi minus hi d ho over ho ho. However you want to remember it is fine. Okay? In using this, there is one assumption. We're going to assume that g of x is not 0. Because if g of x equals 0, the thing's undefined, isn't it? And it's game over. Okay? Let's take a look at something like this. Suppose you have y equals, let's say something like 3x squared minus 9x over x to the 4th minus 17x cubed plus 8. There you go. And you're asked to compute the derivative. So you're asked to compute dy dx equals. Oh, wait a minute. Dy dx is the same thing as y prime, isn't it? Okay. This is a different way of writing it. Okay. As with the previous one, let's kind of lay things out a little bit. This is going to be f. This is going to be g. We already have our blueprint for building our derivative right above it. So it's just a matter now of writing it down. Be careful, there's a minus, not a plus in the quotient rule. Be careful. A common mistake is to throw a plus in there. Real easy part of this is in the denominator. You just take whatever's there. And you do what to it? Square it, yeah. So there's that part done. Then in the numerator, just like with the product rule, remember we were able to write some of it down without having to do anything except just copy it down? Well, we can do the same thing for this and score some partial credit without even doing any calculus. Okay? Notice in the first portion, we need g. Well, that just means copy down whatever's in the denominator, and I'm concerned about having enough space, but we'll see what happens. X to the 4th minus the 17x cubed plus 8. So there's g. On the right-hand side of the subtraction side, what can we just copy down? Just copy down f, can't we? Well, let's see. That's going to be this 3x squared minus 9x. That is good for partial credit. Just correctly writing down the quotient rule, the f prime g minus fg prime over g squared is worth 1 point. Oh, just knowing the quotient rule is worth something? Yeah. Okay. So let's go back to this quotient rule and let's take a look. We need to do f prime. Well, that means take the derivative of that. And the derivative of that's easy stuff, isn't it? What is it? 6x minus 9, isn't it? There it is. Good? Hey, we're almost done. All we have to do now is to write down g prime. It looks like we have room for that. We can extend this. What's g prime going to give you? Well, let's see. The x to the 4th is going to be 4x cubed. 3 times 17 is 51. X squared. The derivative of the plus 8 is 0, right? Don't have to include anything there. And that's done. Yeah, but don't we have to square stuff out in the denominator and distribute stuff in the numerator and combine like terms? No, don't even think about doing that. Don't. Nothing good will happen. Okay? The only thing that can happen is bad stuff, like you break it. Does that make sense to everybody? Okay? And you just walk away from it. You're done. Ta-da! That's all there is to it. The cool thing about the product rule and the quotient rule is once you get down the pattern, they are very straightforward. Okay? It's the same pattern each time. And it becomes very predictable and, yeah, been here, done this. mentioned a couple of times that you need to memorize these two formulas, the product rule and the quotient rule. Actually, that's not completely true. Okay? I've pointed out to you a number of times through the course thus far, and will continue to do so. There are lots of things I don't memorize, but I just kind of have pictures of them in my head. Okay. On this, let's take the product rule first. I know I've never asked this before. If we're doing a derivative, we're really computing a slope. Way to go on it. Okay? And the formula for slope is y2 minus y1 over x2 minus x1. And with this calculus stuff, we're taking the second point and sliding it closer to the first, so we're installing a limit, right? You've heard that enough that, really, Chuck? Okay? You don't have to memorize the product rule. You can derive it every time. You don't have to memorize it. You can use the definition of a derivative to get back the product rule. I can't? I don't have to memorize it? Yeah, let's take a look at what that looks like. If we have something like y equals f of x, some function, times some other function, g of x. Okay? So there's what we're working with. F could be anything. X squared plus 7. G could be x cubed minus 3x squared. You get the idea. Okay, you've seen that a bunch of times. We can compute the derivative by just doing the limit as h goes to 0 of, you've been here before on this, haven't you? You take whatever your function is, and in the first term of the numerator, you plug in x plus h. Does that sound familiar? So all I'm going to do is for the first term in the numerator, everywhere there's an x, I'm going to plug in x plus h. Minus, then, after the subtraction sign, you just use the function itself, don't you? F of x. Or whatever our function is. In this case, it's f of x times g of x. Then, what does the denominator simplify to equal? H. Everybody good? Okay. So, from this, we can get the product rule. Now, there's one sneaky little maneuver we have to do here. And what this sneaky little maneuver is, we have to stick something in here. Suppose I had an equation y equals 7x minus the square root of x. Is that the same thing as 7x minus the square root of x plus 8 minus 8? Well, it seemed kind of weird, but plus 8 minus 8 is really just what? 0. If you introduce something and subtract it, have you really put anything new in there? Well, we're going to do a sneaky maneuver here. And what we're going to do is we're going to stick something in and subtract it all at the same time. So what we're going to do is we're going to rewrite this as the limit as h goes to 0. We're going to still have our first term, f of x plus h, times g of x plus h. I'm going to subtract f of x, g of x plus h. Where'd that come from? Well, you'll see in a minute where that came from, or why we would want to do something like that. And this is something new I've stuck in, isn't it? If I've subtracted it, how do I cancel it out? Add it. So I'm then going to add f of x, g of x plus h. And the very last thing I'm going to do then is, do you see this part that's highlighted? That's still part of the numerator, isn't it? We still have minus f of x, g of f of x, g of x. Way over there at the far right-hand side, and this is all over h. Yeah, this is looking a lot easier than memorizing the product rule already, isn't it? Or not. Okay? This is equal to the limit as h goes to 0. Now let's straighten this out a little bit. We can look at these first two terms. Look at those first two terms. What does each of those terms have as a common factor? Okay, they have f of x, and they have g of, they both have a g what? X plus h, don't they? Could we factor that out of the first two terms? The answer is, well, I guess so. Not quite sure where you're going with this, Chuck. If I factor out this g of x plus h from the first two terms, what I'm going to have left is in this one, still going to have that left, aren't I? So I'm still going to have this f of x plus h. Then, from the second one, still going to have that, minus f of x. It may not be clear to you why I'm doing this just yet, but the algebra there, does that make sense? Okay, from each of the first two terms, I factored out a common factor of g of x plus h. Looking at the second or the last two terms, I'm going to rewrite this as f of x, g of x, which is what it really was before I ran out of space. On that second group of terms, do you see that each of them has an f of x? So I can put down plus f of x times, now, from the second two terms, when I factor out the f of x, this still has a g of x plus h, doesn't it? And this still has a minus g of x. And it's still all over h. This may seem a little strange to you, and this may be something that you're going to need to go back and look at the movie another time or two or three on. Okay? This is probably something very different than you've ever seen before. Welcome to calculus. Now, let's take a little side tour here. If I have something like 2 plus 7 over 19, is that the same thing as 2 over 19 plus 7 over 19? Is it legal to break? Yeah. Okay, Chloe's saying, yeah, that's fine. That'll work, right? We can do that same thing with our fraction that we have over here on the left side of the screen. We can rewrite this as the limit as h goes to 0. I'm going to have f of x plus h minus f of x times g of x plus h. Now it's going to be over the denominator, h, plus, the plus comes from here. Then we're going to have f of x times g of x plus h minus g of x all over h. And this whole thing still has the limit as h goes to 0 applied to it, doesn't it? But what we're slowly doing is we're breaking this apart into two separate fractions, and at the next step we're going to break it apart into two separate limits. Okay, this is going to be equal to with this plus sign, I can break it apart. Does that make sense to everybody? I'm not sure what you mean by break it apart, Chuck. We can rewrite this as the limit as h goes to 0, f of x plus h minus f of x, that whole deal times g of x plus h, all over h, plus, now I'm going to apply the limit to the second fraction, and we're going to have our f of x times g of x plus h minus g of x all over h. Yeah, this is definitely easier than just memorizing the product rule. Everybody okay so far? We're actually getting closer to the end. Okay, so hang in there. We're getting close. It's going to end soon. Equals. Now, here comes a sneaky maneuver on the first one. Yeah, there's always sneaky maneuvers in calculus. Okay. This limit as h goes to 0 applies to the h in the denominator. We can't plug the 0 in there because it'll blow things up. It applies to the f of x plus h, and it also applies to the g of x plus h. If we just apply the limit to the g of x plus h, well, wait a minute, is that legal, Chuck? Yeah, go back to those limit rules that we looked at in the review section. Or wait a minute, that was section 1.1, I think. And I'll tell you, you can break it apart into two pieces with the limit applied to this deal, f of x plus h minus f of x over h times the limit as h goes to 0 of this g of x plus h. All I did was I factored out the g of x plus h. Okay, is everybody good so far? That's about as good as I can get on this stuff. We're going to do that same move on the second term. So this is going to be plus the limit as h goes to 0. On this, I'm going to use that first, the f of x. Then I'm going to do the limit as h goes to 0 of g of x plus h minus g of x all over h. We're almost done. Almost done. Equals. Now, in the first term, realize that we have two factors. We have this chunk, and we have that chunk. The very first chunk, see the limit as h goes to 0 of f of x plus h minus f of x over h. What is that? My head hurts too much to think about anything right now, Chuck. I guess I didn't write it down earlier anywhere. Isn't that just the derivative of f of x? Oh yeah. This piece, this whole thing, is just the derivative of f of x. Okay, so we're going to have f, we're going to have its derivative. Then, for the second factor in that term, say what? This chunk. If we plug in 0 for h, don't we just get g of x? The h goes away and you're left with g of x, whatever that would be. Then we have this plus sign. Then we have this factor times this factor. In the first factor, see it says the limit of f of x as h goes to 0. Is there even an h in there anywhere? So is it going to affect anything? It's not going to affect anything. All we're going to get back is f of x. And then for the last factor, this one. What's that? Yes, sir. That's g prime. You got it. Yeah. So this whole mess here is nothing but g prime of x. And I want to congratulate you. You just survived one of your first proofs in calculus. What we did, yeah, Chloe? Probably not. Okay, I'll give it a little more thought. Some years I say yes, some years no. Now, you have two choices. You can either memorize f prime g plus fg prime. You can memorize it. Or you can rederive it every time, and it's just this. This is all there is to it. It's your choice. I think most of you already made your choice, right? You're working on f prime g plus g prime f. But the cool thing is, you are to the point mathematically where people don't just hand you an equation and say memorize it because, well, you don't have enough to understand where it comes from. Anyway, just memorize it. You're way beyond that. You're to the point now where here's the equation, you can memorize the equation, or you can rederive it every time because you're smart enough to be able to come up with this equation on your own. In fact, if you would have been born a couple hundred years earlier and would have written this down somewhere, you would have been famous. Your name would be one of them that's included in calculus books now. Ah, rats, born a little too late. Does that make sense? What's going on with this? The top portion of this is an outline of what we just went through. So that if you got lost somewhere, or if you copied down something other than the way it should be, that's fine. You've got backup to fix it up. On this, the only difference in the notation is they use delta x instead of h. See it on the limits? It says the limit as delta x approaches 0. Delta means what? Change. The little triangle means change. H means the change, the step size, doesn't it? So they mean the same thing. Two notations mean the same thing. Does that make sense? Are you okay with this one? Okay? I seriously don't expect anybody to, choose that over just writing down the product rule. Product rule is a lot easier to work with. Okay. The last of our secret rules. You've learned the power rule, which is x to different powers. You've learned the product rule, the quotient rule. There are a couple little odds and ends-y functions we need to take care of. Like e to the x, what's its derivative? That's pretty easy, e to the x. No, Chuck, what's the derivative of e to the x? Yeah, it's e to the x. Really? Yeah, it's e to the mathematically, does anybody recall what e to the x is equal to? Well, it's equal to 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, x to the 4th over 4 factorial, plus, and I suspect you can continue the pattern. Where does this stop? It doesn't. It goes all the way to infinity. On your calculator, does it go all the way to infinity on your calculator? Well, no, because it would still be computing the first one you ever asked it to do. It truncates at about 10 terms, something right around in there. Hey, what's that 4 with the exclamation point? Is that 4? Is that what that means? Yeah, we'll go with that, huh? So it's x squared over 2. And I'm not going to go through the rest of them. What does that really mean? David's looking at me like, really? Maybe I need to change sections. What does 4 factorial mean? Well, it's 4 times 3 times 2 times... Oh, yeah, I remember that now. Yeah. Well, I just made mention to you a moment ago that the derivative of e to the x is e to the x. That seems way too easy. But let's take the derivative of it. If we do the derivative with respect to x of e to the x, we're going to get, what's the derivative of 1? It's not that hard. 0. Thank you. Plus, now we do this term. This can be written as 1 over 1 times x. What's the derivative of 1x? Well, what's the derivative of x? 1. Plus, this x squared term can be written as 1 over 2 times 1 times x squared. If you take the derivative if we do the derivative of this, the 2 from the exponent is going to come out front. We're going to have 2 over 2 times 1 x to the first power. What does that fraction simplify to give you? 1. Oh, this is the same thing as x over 1 factorial when you take its derivative. Does that make sense? Plus, this next term is the same thing as 1 over 3 times 2 times 1 x cubed. When you take its derivative, the 3 from the exponent will come out front, and you have 3 over 3 times 2 times 1 x to what power? The second. What'll cancel there? The 3's will cancel, and you're left with 2 times 1, aren't you? So that's going to give you, well, 2 times 1 is 2 factorial, and an x squared. Anybody willing to take a guess at what the next term is going to look like? It's x cubed over 3 factorial, isn't it? No way. Look at this. I always thought this was so cool. Plus, and it just keeps going. And when you take the derivative term by term by term, since it goes all the way to infinity, are you going to get back everything you started with? And what is that you get back? It's e to the x, isn't it? Wow, get out of here. Really? Yeah. This is so cool. Or I got a kick out of it anyway when I first saw it. Still get a kick out of it. The derivative of e to the x e to the x equals e to the x. Prove it. Well, you start out with this first line, and you say, okay, this is what e to the x looks like. Then, just compute its derivative, term by term by term. Jot this down and say, whoa, this is what I get when I take the derivative. But hey, look at there, that's nothing more than e to the x. And I'm right back where I started. The derivative of e to the x is e to the x. Pretty nifty, huh? Two others I want to throw in at this point before we get into section 1.7. The derivative of sine of x is cosine of x. I'm looking at the clock. We've only got about 6 minutes left. We don't quite have time to prove that one, but we could prove that similarly to what we just did with e to the x. We could expand it. That's called a Taylor's series expansion. So if anybody asks you, what'd you learn in calculus today? We learned to compute derivatives of Taylor series expansions. I'll say, okay, I'm not one of those smart people. Okay? But really, is there anything all that horrible to do in that derivative that we just did up in the upper left corner? Yeah, it's horrible. The other derivative, the derivative of cosine. Now be careful. People mess this up. It's negative sine of x. There's a negative there. The derivative of sine is cosine. No negatives involved. The derivative of cosine is negative sine. A negative involved. We've got time for this third one. Real fair question on a quiz or a test. What's the derivative of tangent of x? And very honestly, I could just turn you loose if we had half an hour and say, figure it out on your own. I've got a report I've got to finish writing up and get to Dr. Kegley before noon. I'm going to work on that for the next half hour. You do this. One of the things to keep in mind with trig functions is whenever you get something kind of weird like tangent, rewrite it in terms of sine and cosine. Well, this is the same thing as the derivative of, geez, I forgot, what's tangent? Good. It's sine over cosine. Can you take the derivative of that? Well, not really, Chuck. Chloe's saying, yeah, I can get on that one. Any suggestions on how to take the derivative of this? It's a quotient rule. This is nothing more than a quotient rule. Equals, well, we know in the denominator we're going to get the cosine of x squared. Right? What's the numerator going to look like? Just give me the first part of it, not the whole thing. We'll just do it one little chunk at a time. It's okay, you can look up 6 lines in your notes and read it. That's legal. Isn't it f prime g? May want to jot that down. F prime g minus f g prime. Okay, f prime. What are we taking the derivative here in the first term? Sine or cosine? Sine. The derivative of sine is cosine. Times g is cosine. Minus. Then it says, copy down what f is. Well, that's pretty easy. That's sine. And then take the derivative of the denominator. What's the derivative of cosine? It's negative sine. Negative the sine of x. Everybody okay so far? Okay, so I'm going to rewrite this a little bit. Cosine times cosine is the cosine squared of x. Hey, see this minus here? With that minus, it's going to make it a what? Plus sine squared of x all over cosine squared of x. Hey, can I cancel those cosine squareds and we get sine squared? No, 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 no. Very good, Jacqueline. But there's a sneaky move that you may or you may not recall from trig. Seems like there's always some kind of a sneaky move in calculus to get things done. What's cosine squared plus sine squared? 1. What? Yeah. This whole thing here altogether is equal to 1. This gives us 1 over cosine squared. Now this is the same thing as 1 over cosine times 1 over cosine. Does everybody buy that? Nothing big and tricky there. But what's 1 over cosine? If you just looked at one of these, what's 1 over cosine? What function is that? Seek it and you shall find it. Secant, isn't it? Oh, so that's secant x times secant of x, which is secant squared of x. So what does this wind up giving us? Long way around. The derivative of tangent is secant squared of x. That is real fair game for a quiz or a test, because it's just asking you to remember that tangent is sine over cosine and the quotient rule. Yeah, but I got to remember that sneaky thing, Chuck. Yeah, it goes to 1. Yeah. I haven't shown those to you yet, so don't sweat that right now. If we get time, we'll go through them. Otherwise, just know that they are. Yeah, Chelsea was saying, well, wait a minute. Do I have to be able to prove the derivative of sine's cosine and cosine's negative sine? We've not gone through those yet. So if we get to them, fair game. Otherwise, just memorize them. Okay? 1-6. That's right. And this Friday's your test. So right here in your notes, I don't know what you do. I used to do stuff like this. And then test 1 ends here. You ever do anything like that in your notes? Kind of a handy way to know where the test ends. Yeah, thanks.